Today we have the pleasure to welcome our professors from computer science, Dr. Audris Mockus, and he is Erickson, Harlan Mills Chair Professor. He has PhD in statistics, also applied mathematics undergraduate degree and master degrees. He has a lot of experience in industry. What kind of company? Software company?
AT&T.
AT&T, the labs. And he has done research in software engineering, data science, digital archaeology. And we are working on a very unique, interesting project together between social science and computer science. And today he's going to talk about this project and then machine learning, all this very cool stuff. So let's welcome Dr. Mockus.
Thank you very much for the fantastic introduction. So just so you it's clear, if you have any questions, please let me know. I have sort of two parts to the presentation. One is kind of describing more generally what data science is, and then the second one is talking a little bit more precisely related to the things that Dr. Chen-Fei mentioned just a moment ago, which is about the some of the Twitter analysis. And let me see. So at least I have some idea of the stopwatch. At least I have some idea how much time I have spent. So first, let's start from the question or sort of definitions. So you all know that doing data science can bring you closer to a good job, a well-paying job. So it might be good to know what the hell that data science thing is. So in most cases, nobody cares as long as it pays more. But I think it's worth kind of thinking in it a little bit. So at least when you're an interview, you can sound intelligent. So the reality is that there isn't really a very good definition of what it is, but there are just the practices, and people who do statistics, they claim they are data scientists. People who do machine learning, they claim that they're data science. People who do computer science, they claim to be data scientists as well. Now, so who are these data scientists? This is my kind of attempt to define. So in order to do that, I need to define some other kind of big things, which is knowledge. Knowledge is a philosophical concept, but really in practice, at least in science, it's used as some sort of model simplification of reality that kind of works. So that's what the knowledge is. And so the data science, a good definition of data science is, it's about extraction of knowledge from data. So you have a bunch of data, and then you get some useful model out of that data. So that's really what data science is about. Now, if you didn't sleep during your kind of history or philosophy classes, you probably would realize that science, the purpose of science is also really to measure things and create models. So the mystery is how science is different from data science. Anyone ventures to guess? Go ahead, Nick.
Data science is more mathematical, science is more empirical.
Awesome. So data science is more mathematical, science is more empirical. Great suggestion. Any other suggestions? I'll wait. Yes.
Science typically creates data, whereas data science typically is going to interpret it.
Awesome. So science, I'll repeat it louder. Science typically creates data, while data science tends to interpret it. Very good, very good. Any other suggestions? I need third before I proceed, so somebody please volunteer. Yeah, somebody from the back, maybe? Yes, I can see person with red shirt. I think your lips are moving. No? Yes. Okay.
We go to the Mars, we go to Pluto.
Right, it's discovery. And how about data science? What's the difference in data science? What's your thought?
Data science is based on like, natural science.
Okay, good. So now we have these three opinions. Now I kind of thought about that because that was a puzzle. So I came up with something that sort of probably encompasses all three to some extent. So and basically the difference between science and data science is really not that big to my, because you actually do discoveries in data science as well. So the difference is what kind of data you handle it, right? In traditional science, you carefully design measurements which are based on very expensive stuff like telescope or whatever, that you spend a lot of money to make sure that you know what you measure. And once you have the measurements, you basically you do the science. Now in data science, really mostly you deal with some crappy data that's been collected as part of some ongoing process, which wasn't really designed to do any sort of science. And so really the role of data science is extracting stuff out of that data. So well, anyway, so I define evidence engineering is also some other thing. It's not so important. We can sort of skip that. So let me give an example. Like always, one thing is to define something, another is to give an example. So let's do an example. So let's think about we study, say, temperature or climate. Climate is very popular thing these days. Study climate change. In order to do that, we need to measure something as basic as temperature. So traditionally, you have a science field called meteorology. It measures temperature, puts the weather stations all over the place, including in the Arctic, Antarctic, Then other thing is that each weather station is very carefully designed. It's not cheap. It's got to have a temperature sensor. It's got to be shaded from sun. It has to be freely ventilated by air. All sorts of restrictions. So there's like pages and pages that describe on how this sensor, where it should be placed. And then historically, when these sensors didn't provide automatic data, people would actually collect the measures at specific times of day, so that you're not getting confused about, when you measure temperature, say at noon is not the same as measuring at midnight. So they would have specific times of day where they would go and collect these measures. So once you have these measures, you know exactly what's being measured. You have some certainty that each measurement is probably accurate. Well, then you basically, what you do science. You come up with climate models that predict or estimate the kind of distribution of the measurement and try to sort of understand climate change. So that's kind of the traditional science approach. Now, we can take the same problem and take a look at it from sort of data science perspective. And that will be a very, very different way of looking at that. For example, we could say, well, putting these weather stations is expensive. We cannot put them everywhere. But we've got these wonderful companies like phone companies. We've got these wonderful companies like Facebook and Google. They collect all sorts of data. Maybe we can use their data to somehow do this climate modeling, right? So how would you go about that? Well, so first of all, what kind of data you have? Well, one of the data that's pretty popular is people carrying the mobile phones with them all over the place, right? So wherever people are, probably you're going to get some mobile phones there. Now, the problem with mobile phone, it's not a carefully calibrated weather station, right? So it doesn't even have temperature sensor, but it has a bunch of other sensors, right? So maybe we can use these other sensors somehow to measure it. But furthermore, there are other stuff, like you don't know the context, right? Is the person right now outside or inside? It's not so interesting from climate models to see what indoor temperature is. It's more interesting to see what's the outdoor temperature, right? You don't necessarily, certain times may be missing, certain locations may be missing, if there's no base stations there. Some of these sensors may malfunction. We don't control people's mobile phones. So there's all sorts of stuff. But anyway, at the end of the day, what the hope is, you have a bunch of people, they walk around, and they produce, and then produce, from their mobile, different kinds of mobile phones, they produce some signals. We measure these signals, and somehow from these signals, we try to figure out what the temperature is and what the weather patterns are. So how would you go about that? Well, it's not so simple, right? So, as I mentioned, the mobile phone doesn't even measure that temperature, right? So we need to infer that temperature from something else. Well, one way is we can hire a bunch of students like you, put them in the cold room with a mobile phone, and sort of measure what signals comes out, and then put them in the hot room and measure what kind of signals come out, and then maybe create some data laws that relate, how the various measurements on the phone reflect the temperature, the ambient temperature in the room, right? Then we need to figure out, okay, so now the person came inside, how do we detect that? Now the person maybe is driving in a car, maybe we can detect that as well and sort of separate that, because that data is not interesting from climate model perspective, right? So these are some of the steps we can go. Then we come up with these data laws that relate the sensor measurement back to original temperature, segments it, decides which measurements to ignore, which measurements to correct. And then at the end of the day, we could say, okay, now we're collecting measurements from these two kind of people in the summer afternoon, resting out, and these are the measurements. We apply our sort of algorithms, and we say, oh, that's the temperature that probably is consistent with these kinds of measurements. Okay, so that's really a data science approach. And again, we have tons and tons of these measurements because there's so many more people than weather stations. But again, they are problematic. So the data science is really about getting from this problematic data to the data that you can use for actual science. Any questions so far? Okay. So there's kind of, with temperature data, at least we know what we're trying to measure, right? So we're measuring the temperature. So that's not so difficult for us to say, okay, let's put the student in the room, put the temperature to a certain degree, and try to find what's good, what's bad. In most cases where we try to use this data to do data science, we really don't know what the right answer is. Suppose a person types something into Google search and a bunch of things come back. Is it the right answer? Is it the wrong answer? Who knows? It's really very difficult to measure. So that's one challenge, right? In entertainment, again, there's a lot of AI going on there trying to predict what people will enjoy. But if you change slightly, is the game, that less enjoyable? How do you actually measure that? So the measurements of really what we're trying to do are also a little bit different than traditional science. In social life, like, Facebook, they typically what they do, they measure it by revenue, like how much they can sell in terms of advertising. But does it really improve your social life? Not so clear. So anyway, so these are various areas where these problems may occur, and we don't even know how to sort of do this modeling, because not only the measurements are crappy, but we also don't know how to even know when the right measurements aren't there either, right? So that's kind of a big challenge in a lot of data science. So if I were to summarize the differences between traditional measurement, experimental measurement, and operational data, basically there are three basic things. One is that we have these multiple contexts. That is, we could get the measurements for people being inside and outside at the same time. And we really need to know that, because the ones from the inside are not very useful for climate models. They might be useful to understand the people's utility bills, and many of you work on that, but they may not be very useful for climate change. So if we're measuring that, the second part, they might be not particularly useful, and we need to do that somehow, right? Second is that some of the important things may be missing. And one example I always give is the story of this statistician, Walt, who was consulting he was anyway, so it was kind of worse scenario, and British Air Force was measuring the planes that come back from the war, from the bombing raids, and they're looking where these planes have been shot. So they're basically looking in the fuselage and wings where the holes are. And for each plane that comes back, they draw on the picture where the holes are, superimpose over many, many planes, and then they find areas where the planes are hit the most often. And they were about to do the following. They were about to go ahead and put reinforcements in the areas of the planes where they are shot the most, where they observe a lot of holes. And this Wald guy says, wait, you're really not doing the right thing. It's probably not the right place to put reinforcements. You should put reinforcements and where he suggested to put reinforcements. Where they weren't being shot. So now, why would he suggest that?
Because they were survivors.
Right, so the reason, as Nick pointed out, is because we're actually looking only at the planes that come back, right? So we're not looking at the planes that went down. So the planes that come back, probably you want to put the repair where you never see holes, because presumably if the plane is hit in that area, it never comes back, right? So that's kind of the missing data kind of problem that is very common in operational data, right? And then finally, there's a lot of data is just plain wrong, bad, and so that needs to be somehow either corrected or removed. Furthermore, these operational systems are continuously changing. So we'll talk later about the Twitter. And again, the way people use Twitter, the Twitter itself keeps changing over time. So whatever we observe maybe in the past might not be a reflection of what will happen, of the right way to do the measurement now. Measuring and defining accuracy is pretty difficult in certain cases, like in measuring maybe emotion or measuring correctness of query, and there's a lot of potential for misinterpretation. So this is kind of data science challenges. These are real kind of, that's my attempt to sort of focus on what the problems are. So now I went through this part. I want to go to the other part, which will be on the web page. And so maybe we can, if we go to the browser.
Yeah, I just
And maybe we can make it like presentation mode or something. Yeah. Awesome. Thank you. Okay, so now that we know what the data science is, that essentially this is the main challenge is really get from the crappy data to good data. Let's talk about specific application, and this looking at the Twitter data. And so this is a project that involves a lot of students, and I tried to list them all. I forgot some of them. Actually, Natalie is not there, but so I will, so this has been going on for a while. So one of the things that, as you can imagine, with this operational data, is that there's a lot of things need to be done to it before we can actually use it for anything. So data management is kind of like pretty important, and I'll describe a way to go about that in the next few slides. So in this particular study, what's interesting is studying the tweets pertaining maybe to specific disasters, tweets pertaining to specific topics, right? And anyone who works in data science knows that the data comes in tables. The tables are typically come in CSV files or Excel files, right? So very soon, after you study a bunch of stuff, you realize that CSV files are not really best way to share the data. First of all, you forget which CSV file was used for what. If you have a very large CSV file, it's kind of difficult to load and navigate. There's different spellings of these tweets, different quotes, etc. And then the you can't even read the file. Different people may use different formats, etc. So the solution was to put everything into a single database. So that's kind of a typical way of organizing that. And the reason for this particular type of database is because it sort of is well suited to storing JSON files, which is how the tweets are come for the most part. So, so next thing is sort of organize the collections in such a way that, well, you store in the database, still at least you need to find what you need. So, so there's a variety of collections in this database. Status is basically what the tweets are, information about accounts. So these, whenever the tweet happens, there's also a person who tweets it, to whom that tweet goes to. So that's a separate thing, and you can get information there. Also geolocation of these tweets, and then and in particular, there's some several databases that are around. Just over 3 months, there's about 5 million tweets that mention climate change, some keywords related to climate change, and 45 million that mention power. Though in this case, it's not just electric power. A lot of that is just about more sort of power in an adjective sense. So so here's some description of these databases. So the naming is kind of so MongoDB has this concept of database and collection. So the database is all Twitter, and collections would be like statuses, Irma. So it's a collection containing tweets about Hurricane Irma that were previously stored in CSV files. So status is climate change A. So A stands for API, C stands for CSV. So basically, we keep information in the name where it was important, because at this point, we don't even know how these tweets came about, etc. So these are some of the examples of how you can find information there. So now that we have kind of infrastructure where we can store information, we also need some additional ways of getting the information as well. So one of the problems of using Twitter, if you don't know it yet, is that when you use its streaming API, you can collect a lot of tweets, not all, but a lot of tweets. The problem is you don't have any history. So if you say, what kind of tweets happened 3 years ago, there's no way for you to get that. So there's another approach to get that information about the tweets, by figuring out, okay, so we only care about the tweets that came to this user or came from that user. So you basically go to find the users, Twitter users that you care about, and then for each Twitter user, you can go to their web page, essentially Twitter web page, and that web page has full history of the tweets that happened to that user. So in order to do that, we need to identify these user accounts. And in particular, for this study, we looked at local, national media, nonprofit, government, and utilities. And there's several steps in identifying these accounts. I'll talk a bit about two options. And then and once these accounts are identified, then we can just scrape these websites and it retrieve all the tweets that pertain to these accounts. Now, again, these are not the same as streaming API tweets, but the advantage of these that we can go fast in history. With streaming API, we can collect only right now. And if we miss something, then, that's it. Okay. So once we have the tweets, we need to do something with them, right? So the next step is to try to extract some information out of them. Again, just like with the situation with this phone, that we have some measurements, but we really don't have what we care about, right? So we don't have the temperature. Well, in this case, we really want to understand different types of content. And some of the interesting stuff about the content is, well, so some of the things in content would be like what the location is, etc. But there are other things that are even more interesting, especially in situations like disasters. That is how people react to things. Now, there are certain things that people care about, like emotions, opinion, and sentiment. Now, the way these things are defined, is typically implicit. So, for example, emotion is clearly defined state of feeling that changes a person's thoughts and behavior. Opinion is judgment, a viewpoint made by someone about a topic. Sentiment, expression of an opinion or emotion towards a situation or event. So you can see sentiment is really based on these two. So it's not so simple what it is. Now, then people, talk about sentiment analysis. So basically labeling text based on the sentiment they think. There's another term, opinion minding. So there's a variety of things which are kind of used interchangeably in literature. And so you need to be very careful about what you're talking. And so some of the results of this effort was to kind of basically say, yeah, here's what the actual terms is, and sort of more rigorously define what opinion, sentiment, and sentiment analysis should be. So once we know what we're looking for, then we need to try to basically to extract, say, sentiment or something else for the, and there is sort of generally traditional text analysis has sort of certain types of ways of proceeding. So the most historic text analysis would be keyword search. So how many of you know what keyword search is? Well, search keyword, describe it, maybe somebody from the back, anyone willing to tell what a keyword search is?
Control F.
Yeah, that's Control F, but what does it do? It looks through the text and find all the instances where that specific word that you typed is there, okay? So these are the very basic approaches, is basically lexicon based. So basically you have a dictionary and you're saying that, well, if any of these words occur, if all these words occur or something like that, then I'll select that document is relevant, otherwise it's not. Now there are other approaches that are quite different in nature. So most of the machine learning approaches that we use, and they kind of tend to be formed better than the traditional ones, are a little bit different. Basically what you do is you provide a large set of labeled documents. So you basically say, so you give, say, movie review, and then somebody looks through and says, well, the review is very negative. That means the movie sucks really bad, And so you collect thousands of these reviews, say, or product reviews from Amazon, and then somebody looks through them and says, well, this is a bad review, this is good review, right? So then then for each of that review, you basically assign that label, that sentiment. Then you feed that to some learning algorithm and classifier, and then it can actually, you feed that classifier, then it learns how the people sort of rated these movies. And then if you give some new review, then it will very accurately tell if that's positive review or negative review. Essentially, it will tell you what the sentiment is. So that's kind of the machine learning approaches. And then there's some hybrid approaches as well. So I'll discuss that in more detail. Again, one of the things that people perhaps don't talk about is that sentiments are not really easy to describe. So, for example, one of the biggest problems with these machine learning approaches are that when people talk about sentiment, they only refer to the sentences that actually might contain a sentiment, which are an expression of opinion. But actually, a lot of statements that you see in Twitter and in text have no opinion whatsoever. They're just statements of fact, statements of action. And so how do we sort of separate these? Okay? So that's another problem that one has to face. So again, so for example, the opinion can be expressed only if the statement is subjective. If it's an objective fact, obviously it's not an opinion. So how do you separate them? Anyway, so there's a variety of these ways that one can go about extracting sentiments from defining and extracting sentiments. So here's some very examples of actually. So we're not talking about any machine learning so far. We're just talking, what is a sentiment? If you see a sentence, can you tell what sentiment it has? Okay, so we just, because that's a very important part. Unless we can do that, we don't know what happens once we actually feed that labeled data to the machine learning. So the first step is basically, so these are some examples of sentiment. This could be a good sign. I just spotted power crews outside my house. Okay. So this is kind of this is for some reason marked negative. I'm not sure, but there was some coding scheme that sort of, and this, thank you for providing amazing service. Sorry? Yeah, I think these are mixed up. Yeah, right. So, and then, so, yeah, because, so this is neutral, so there's no sentiment. So there's an opinion, but there's no, it's neither positive nor negative. And then this is the negative. So this is some sort of expression of anger or something like that. So anyway, what I'm trying to say is that even if you define something very carefully, there's still a huge effort in trying to tell what it actually is. Now, once you go to emotions, then it becomes even more complicated. So you have tons of emotions, like sentiment could be positive, negative, but emotion could be much more complicated. And as always, there's many more negative emotions than positive emotions. That's not a surprise, right? So now that we sort of went through and presumably spent this time collecting the data, cleaning data, organizing data, coming up with labels, so now we can go and address the next point, which is that for any non-trivial amount of data, we have maybe millions of tweets. We cannot manually go through millions of tweets when a single tweet is painful to classify, right? So what do we do in this case, right? So because manual classification doesn't scale, we really need to use manual classification to train machine learning models. And that's a very typical situation in machine learning. So all the successes of machine learning lately have come because you have these databases of stuff that's labeled, massive databases. Now, if you ask the question for which there are no massive databases, you're stuck because machine learning cannot help unless you train it, right? So it's like a very powerful, I don't know, pony, but it doesn't know any tricks. So you cannot win any sort of competitions until you sort of impart that knowledge into that thing. So the typical approach is, if I need domain-specific area, you essentially start with manual classification that focuses on training machine learning models. So now we'll talk about machine learning models on text in particular. So how many of you have applied any text analysis besides typing the Control F button? Well, that's also, I mean, as you can see, that's also text analysis, but it's a fairly basic form of text analysis. Okay, nobody wants to admit, but I'm pretty sure you know a little bit about that. So one of the key things with text analysis is that all the techniques in machine learning or anywhere else in mathematics, they deal with numbers, not with text. So the first step that you need to do is to convert text into numbers. So there's various pre-processing steps usually to exclude, just like I mentioned, exclude irrelevant data, like articles usually are not very important. You may words, plural words maybe not mean the same thing as singular, etc. So there's some normalization that people try to do on text. But suppose you did some normalization. Then you need to do what's called vectorization. So vectorization is converting text into numbers. And as the word says, you map each word into a specific vector. Okay? I hope everyone knows what the vector is. It's just a collection of numbers. Okay? So the simplest vectorization is what's called bag of words. The bag of words basically says, okay, language has, I don't know, 100,000 words that are used. So we will encode every word as 100,000 length vector. So we'll order all the words from first to the last, and then the position corresponding to that word will be 1, and all other positions will be 0. So that vector will represent the word, say, horse is in position, I don't know, 10,021. So the vector for the horse would be all zeros until 10,021, then 1, and all the remaining ones will be zeros. So now we have each word represented by very, very long vector. Okay? So that's the bag of words representation. Other representation, it was called term frequency inverse document frequency. So people realize, so the bag of words representation is if you search, say, for word horse, you press Control F on your screen and then type in horse, and it finds all the instances of the horse, right? But maybe you are looking not just for the horse, but animals that are mares as well, right? It won't find that. So that's a problem. Also, if you search for something that's very common, like article that, it will occur in all the documents, right? So that's not going to be very useful. So TF-IDF is a kind of weighted representation of words where it still uses the same long vector, but it basically says, let's count how many times the word horse occurs in this document. So instead of 1 in the horse position, it will count the number of times it occurs. And then it inverse document frequency, it downweights it, divides it by the number of documents the word horse appears. Now, what's the idea behind that? Well, the idea is that, for example, article that will occur in all the documents. So it's not very useful to finding the document that you care about. So, and so that means this inverse document frequency will be huge. It will be in all the documents that you can observe, right? Because in English language, that's a very common word. And so you essentially downweighted by document frequency and upweighted by how many times it occurs in the document. That way you can sort of get a little bit better keyword search than before. It's still a keyword search, but it's based on this slightly different ways. Now there are other embeddings, and if we have time, we'll talk about them, that are a little bit more complicated, and they do a more interesting thing. So again, if we were to sort of go through the process, we have this tweet that we want to classify. So first step of pre-processing, we'll throw out common words like is, and then so leave also common word we. So we'll leave 1 and 2 and leave classify. So essentially after cleaning, we get this collection of words. Then we map that into the say bag of words representation, and then we find similarity to all other documents. So that's the numeric embedding of that particular tweet. So we have all these 4 words. So we have these vectors. We can add them together. We can treat them separately. Okay. Any questions so far? Okay, so I have a few more slides. I'll try to finish because I think I'm close to 40 minutes. So again, so this is our MongoDB. So we get the data from streaming API. We also import data from pre-labeled data sets. So people in machine learning, it's very important to know about what data sets are available, because each labeled data sets you can train your model and use it to do prediction. And then we have also source-specific historic scraping that I mentioned before. So then we do pre-processing, and then we can sort of do different levels, essentially do embedding, and then do classification. So these are the 3 steps, and we'll go in more detail over each one. So what is Doc2Vec? So Doc2Vec essentially is converts all the words into numbers. Now, the difference between that bag of words representation that I mentioned, it has each vector that's, the length of number of words in the corpus. So all the language may have 100, 200,000 words. So that would be a very long vector. If you look at the corpus like Wikipedia, it will probably have that much or more words. So Each, if you use the bag of words implementation, you have very long vectors. Now, very long vectors are difficult to work with, and they have problems, right? So Dr. Beck is actually creates this much more compact representation of maybe 100 or 200 length vector. So each word is represented by a much shorter vector, right? So the idea of that embedding is as follows: that word that means similar things will be represented by similar vectors. So for example, if you look at, and the way you look at the similarity is, again, you look in the numeric sense. So in text analysis, so for example, you have the word burger and you have the word sandwich, and you calculate the distance between them by doing cosine similarity, basically dot product divided by the norm. And in this case, it's 0.6. So, at least based on some embedding of these. So that shows that it's actually, they're pretty close. So these words are really not far apart. But they have some, burger would be very different from perhaps a horse, because first of all, you don't use horse meat usually for the burgers. And second, it's a different object altogether. One is food, another is an animal, right? So that's kind of the idea of doing that. And these different, Dr. Beck is one particular embedding that's really particularly effective. Not only embeds the data, it also embeds the labels of the data as well. So these are two things that it's capable of achieving. So, as I mentioned, is that one of the first steps in order to extract sentiment analysis is to, first of all, unfortunately, if we apply any of these of machine learning algorithms on any text, we'll find that they perform really, really badly. And the reason they perform really badly is because only maybe 20% of the text contains sentiment, right? So when you're trying to predict sentiment on sentences that do not have it, right? So by chance, you predict either positive or negative sentiment, but there's none. So one of the approaches you can use is to actually label the data that says it has sentiment and does not have sentiment, and then basically fit a special model that says, is it the relevant data set for sentiment analysis or not? So essentially do two-level classifier. First level classifier says, let's find only the text that is likely to contain sentiment, and then we're gonna predict what the sentiment is. And anyway, so this is the way. So the similar way, as I mentioned, is that earlier, is that we can also apply it not just to detect sentiment, but to do anything else. In this particular case, what we're trying to do text analysis to determine if a particular Twitter account belongs to a news organization, right? So we do want to have, there are millions of Twitter accounts. We can go through all of them, but we don't know which ones are for news organizations or which ones are not. If we want to identify that, we need a sample that has labels, and we can use the Dr. Beck model to basically say, in this case, not to do sentiment analysis, but to predict whether or not something is going to be a news organization account. So you can essentially predict the types of users as well. I'll probably so this is a little bit too much detail, so I'll skip that. So now we went through some examples of how to apply text analysis to do segmentation and classification. After the data science is done, we can actually, essentially, we do three things: data context recovery, we do data augmentation, we may do data correction. Then we can start real science, which is basically now we have these tweets, we can calculate what frequency of different tweets are over time, and model real phenomena. So for example, this shows percent of tweets on a specific topic. And we see that, before the Hurricane Irma, most of the topics were about request, essentially response to customer requests. So customer goes to Twitter account, says, oh, I have some problems with power, and that's what the typical kind of boring communication on Twitter between power company and customers are. But once the hurricane started, you suddenly see very different kind of behavior. Different topics came to the top: complaints about lack of power, response, et cetera, et cetera. And it's sort of, and then towards the end, we see tips, advice is kind of peaks towards the end. So you can sort of observe very varied response to a customer, interaction between utility and the users during particular hurricane. Well, anyway, on this I wanted to stop. If there are any more questions, I'd be happy to go into more details on any of the topics that you've seen, or maybe other topics.
Talk about positive and negative tweets. Have you had any issues with sarcasm?
Yeah, so that's an excellent question. So there's a variety of problems with positive or negative. For example, just to give you an example, the word good in general, if you sort of treat it as, embed the word good as a separate vector, right? It means, positive, obviously positive sense. Now, if you happen to have not good, right, that same word means a totally different thing. So there's several ways to deal with that, and that's why the sentiment coding needs to pertain to entire sentence, not just to a specific word. So sometimes you can do techniques at the lower level. You look at bigrams, so encode not individual words, but sequence 2 words at a time. So if you see not good very often, you treat it as one word. So you would have good and you have not good. So these would be, treated as different terms. They will be in a different positions of that space. Another approach is to again use the labeling to detect sarcasm. So there was an attempt to do that, but the reality is that let me see. So in this case, the sentiment was detected, and sarcasm, actually knowing the sarcasm level helped to predict the sentiment more precisely for obvious reasons, right? So something might be says, some positive statements that are positive if taken on face value. There's no way an algorithm can figure out that it's going to be, not negative, but it would be negative if it's a sarcastic statement, because, in sarcasm, usually you mean opposite thing of what you actually state. So a human radar could detect sarcasm, and you can actually train the algorithm to learn what sarcasm is. It's not, I don't think that there's a lot of progress in that area, but again, you need a very large corpus of text in order to train to recognize sarcasm. Did I answer your question, by the way? Partially. Okay.
But how can machine know? How can a machine learn sarcasm?
Well, how humans recognize sarcasm?
Because we are smarter than machine.
Well, the argument these days is if you have large enough database, the machine will be smarter than any human, right? Because the humans learn from examples, right? So if you give enough examples, the machine will actually does a better job even at facial recognition than humans, simply because, if you have enough data. The problem, though, is what we face is that most domains, we don't have enough data. So, sarcasm in one domain might be different than in another domain. So sometimes you can't even produce that data. But that's really the assumption is that if there must be pattern, and that pattern you recognize. And so a machine can recognize it as well if it has enough information. Great questions. Yes, Nick.
This is kind of related. How does the machine account for things like code law, where it's like at its extreme difference, but it's impossible to tell between a parody of an extreme opinion and a genuinely extreme opinion?
Well, so again, so there's nothing in Doc2Vec or any machine learning tools that actually learns that, right? So the only way, so these approaches are extremely stupid in its nature, and I need to add a little bit of a story to that, is that traditional text analysis, in the 80s, was focused on grammar. So people thought, if we could understand the grammar, then things like not good will be rather obvious, right? So if you put some sort of qualifier in the beginning, then it changes the meaning of the entire sentence. So somehow, if we could put everything in the schematic sense, we would solve the problem. It turns out that natural language, there was no progress basically for 20 years. And people found that, the best way to do the training is when you really do a very stupid classifier, but you just feed it a lot of data. So to answer your question, is nobody knows what exactly makes these certain models work better than other models. That they're essentially black box. And so it's kind of right now, all the machine learning field is really very much of it's not science, it's more of a black magic, or actually, you kind of get these heuristics about, whether you should do cleaning, where you should do that, what kind of sampling should you do, what kind of data you need to collect. So it's very experimental, very kind of hands-on, experience-based thing. So even if you take classes and understand perfectly well how machine learning methods work, there's a good chance you won't be able to do a good job in practice, because that requires a lot more. Yes, please, question.
You mentioned that there's kind of art and there's heuristics involved. There are people that use machine learning to siphon through the heuristics in order to control other machine learning algorithms.
Yeah, there's lots. So that field is really wonderful. So so for example, so the question is, a lot of heuristics is about how to make the algorithm learn faster with less data. That's really what if you have enough data, you don't need to worry about anything. But usually you don't have enough data. So the question is, how do you make? So one of the heuristics would be, how do you create additional examples from the data that you have? So there are these what's called adversarial networks, which essentially have models of how that machine learning algorithm works, and tries to kind of trip it, generate input data that trips it. So for example, there are these very good machine learning algorithms for image recognition, but then you change a few pixels and they're totally confused, right? So one of the heuristics would be, if you could sort of figure out, run two machine learning algorithms, one's trying to trip another one by modifying the data, then that, the one that, that's learning would be, would have a much more robust, and would get a better, I'm just giving an example of that heuristic. Now, so that's one answer. Another answer is, so in this case, people essentially created this kind of multi-heuristic approach to generate negative examples, and that way to train it. People with CNNs try to say, okay, so can we visualize how that neural network works? So that's another way, but it's very, it's really, really difficult. So I don't know of any kind of really good examples that you could just go and it would show which heuristics to apply, have some systematic way of describing that, if that's the question. But, hopefully in the next 10 years that will happen, but because people definitely are working in this area. So maybe you'll be the one who does that. Good questions. Okay. Any more questions? Or we're out of time?
I think so.
Okay, thank you so much.
Thank you.